This is going to be our last video for our Apex Pre-Calculus series. We're going to be doing exercises from 3.5. We are going to be solving trigonometric equations using arcsine, arccosine, arctangent. We're also going to be talking a little bit about trigonometric identities and solving equations where the variables are trig functions. So just a slight overview of those concepts, cover them much more in depth in our pre-calculus course at the school that I work at, or we can talk about some of those topics outside of these videos if you would like. All right, number one, sketch the right triangle whose angle theta can be associated with negative pi over 6. Negative angles are going to be measured going clockwise instead of counterclockwise. So we're at negative pi over 6, means we're pi over 6 or 30 degrees below the x-axis here. That means that this is a -1 going down. This is a √3 here, and this is 2 here, and it wants the sine of that angle theta. So theta was that negative pi over 6. Sine is opposite over hypotenuse. Explain why the arcsine is restricted. This is going to take a little bit of an explanation. But bear with me that the sine curve looks approximately like so. I need to use quadrant 1 and another adjacent quadrant that's going to give me all of the possible output values. So I'm going to do that by using quadrant 4 here. This part of the graph is in quadrant 4 and quadrant 1. So I get all the negative sine values from quadrant 4 and all the positive sine values from quadrant 1. We're always going to get the positive piece from quadrant 1 and all of these inverse trig functions. So that's going to make this a one-to-one function when I restrict it to this piece that I'm going to color in a little darker here. In fact, let me change colors and let me, this piece that I'm coloring in red right here is what we're going to call the capital S sine function, and that means that it has a restricted domain. So capital S sine is going to have a domain of negative pi over 2 to pi over 2. It's going to have a range that's the same as little s, sin(x), from -1 to 1. They keep the same range. And what I'm going to do is I'm going to take the inverse of this by switching x and y, and I get little s inverse sine, or another way that this textbook is going to write that is going to be arc sine, like that, and its domain is going to be the range of capital S sine, and its range is going to be the domain of capital S sine, because again, when we find inverse functions, we switch x and y, so we switch the domain and range. So that took a little explanation. I hope that that makes sense. Explain how the unit circle helps us evaluate inverse trigonometric functions. So when we get these down here, we're going to be able to look at the unit circle to see where those values are positive or negative in the given restricted areas, find the angle that goes back to those values. You have to have sine, cosine, tangent, secant, cosecant, cotangent values that are on the unit circle, though, for that to be helpful. Otherwise, you're going to have to use your calculator to help you out with that. Number 4, true or false, sine squared of 5x plus cosine squared of 5x is equal to 5. That's false, because sine squared of anything plus cosine squared of that same anything is always equal to 1. So we're going to change this to say sine squared of 5x plus cosine squared of 5x is equal to 1. That's going to be the corrected version of the statement. On to number 5. Number 5 asks us to find the arc sine of √3/2. This is positive, so we're going to be in quadrant 1. The sine value is √3/2. So across from the √3 is pi/3 in my special right triangle. This is pi/3. I could use the unit circle, but I'm going to be drawing more triangles in this one since we did the unit circle last time. And I want to focus on those triangles that are those trig triangles that are important to us, especially for physics class. Arc cosine. So cosine is going to be restricted not to quadrants 1 and 4, but to quadrants 1 and 2, because I need to focus on the x values. So my angles are going to be between 0 and pi. So I'm going to be over in quadrant 2, and I have a cosine value that's -√3/2, and that's 1. This reference angle is going to be pi/6 here. So that means that this angle here is going to be 5 pi/6 to get me over there, because I'm pi/6 away from pi. Number 7, arctangent is of -1. So we're down here in quadrant 4, and this is going to be -1, 1, √2. The ratio of opposite over adjacent is -1 there. This is a 45-degree reference angle, or -pi/4. 8, arctangent is going to be √3. So √3/1, pi/3 is the reference angle. Number 9, I want my arc sine to be 0. So between -pi/2 and pi/2, the only place where the y value is 0 on my unit circle is going to be 0 degrees, or 0 radians. Actually, we're going to be answering in radians here, not in degrees. All right, use your knowledge of trigonometric functions and their relationships to right triangles to answer the questions in exercises 10 to 19. We're going to be using some special right triangles here, such as 3, 4, 5, 5, 12, 13, 7, 24, 25, 8, 15, 17, and so on. But there's some special right triangles that we need to know off the top of our heads for trigonometry, and we're especially going to be using this one quite a bit. So in this problem, it says consider the right triangle whose hypotenuse is going to be 5 inches, and there's going to be a given side that they want to be across from our angle that is going to measure 3 inches, and they want us to find the tangent of that angle. So we need this missing side since we need opposite and adjacent. This is a 3, 4, 5 right triangle. So the tangent of that angle is 3 to 4, or 3/4. Consider the right triangle whose hypotenuse is of length 5 inches. And then there is a side that is 2 inches. It's across from the angle that we're interested in. I always want my angle in standard position in the lower left-hand corner. And then they want us to find the sine of this angle. So the sine of theta is going to be opposite over hypotenuse is going to be 2/5. Now we're going to imagine a circle with a radius of 2 units centered around the origin. So we have radius 2. What are the angles associated with the intersections of the circle and the line x is equal to 1? So x equals 1 right here. We want, what are the angles here? If this is 1 something, and this is 1 something down here, right? We want to find these angles here. So this is 2, and this is 2, and this is 1. So this is going to be √3, and this is going to be -√3 because these are special right triangles that I recognize. This is going to be pi/3, and this is going to be -pi/3. So my angle 1 is going to be -pi/3, and my angle 2 is going to be pi/3. Discuss the right triangle that can be associated with theta equals -2pi/3. So that's going to be over here with a reference angle of 60 degrees here, or pi/3. We're going to be down here in quadrant 3. So we're going to have a -x and a -y. This is going to be -√3. This is going to be -1, and this is going to be 2. So that's how I would draw that. Number 14 asks me to sketch a right triangle that can be associated with 5pi/4. So that's going to be down here again in quadrant 3. My reference angle is going to be pi/4. So this is going to be -1 and -1 and √2. Because it's a 45, 45, 90 right triangle. Those are the proportions, 1, 1, √2 for a 45, 45, 90. Number 15 asks us to sketch a right triangle that can be associated with -pi/6. So this is reference angle pi/6 down here. This is going to be -1, √3, and 2. Number 16. Suppose that the sine of a triangle is 3/5. What are the possible values of cosine? So if the sine is positive, it could be in quadrant 1 or in quadrant 2. I don't know. So we could have this triangle or this triangle that have a sine of 3/5. We could have 4 or -4 for our other side. So our cosine of theta could be equal to, our theta could be either this small angle or this big angle. Our cosine of theta could be equal to 4/5, or cosine of theta could be equal to -4/5, depending on which triangle we're looking at here. Oh, I didn't evaluate all of these that I was supposed to. So I think you can, though. Let's just go back and let's say -2pi/3 here. That this was pi/3 is my reference angle. This was -√3, -1, 2. They ask us for tangent. Tangent of -2pi/3 is going to be √3. They ask us for 5pi/4. It's down here. And it was -1, -1, √2. And they ask us for cotangent. So cotangent of 5pi/4 is going to be adjacent over opposite. That's going to be 1. And then I have the -pi/6. And this is -1, √3, 2. And they wanted me to find sine. Sine of -pi/6 is going to be -1/2. We already did number 16. Number 17 says suppose that cosine is 5/13. 5/13, this is a 5/12/13 right triangle. So I'm going to have a positive cosine value. So I'm either in quadrant 1 or 4. So what are all the possible values of tangent? Tangent of theta could be equal to opposite over adjacent is going to be 12/5, or tangent of theta could be equal to -12/5 if I'm down here in this triangle instead. Suppose that tangent is equal to -1. Tangent is -1. I'm on this line. I'm either in quadrant 2 or quadrant 4. For my reference angle, -1, 1, √2, 1, -1, √2. This is -π/4, or this is 3π/4. Something like that. They want to know what are the possible values of cosecant. Remember that cosecant theta is equal to the reciprocal of sine of theta. So it's hypotenuse, or r, over opposite, which is y. It's r over y, so cosecant could be equal to √2/1, which is going to be √2, or cosecant theta is equal to √2/-1, which is -√2. That was number 18. Number 19, classic calculus problem involves a ladder leaning against a wall that's going to be slipping. Base of the ladder starts slipping away like this from the wall, causing the top of the ladder to slide down the wall like this. If you know the ladder has a length of 13 feet, find the value of cosine when the base of the ladder is 12 feet away from the wall. So here's theta, and they want cosine of theta is going to be equal to adjacent over hypotenuse is going to be 12/13. If you needed this other side, which we didn't need over here, this would be 5 feet, that it would be from the ground at the time, but it's 12 feet away from the base of the wall there. That is everything for this set of videos. I hope to be able to do some more pre-calculus problems from the OpenStax pre-calculus textbook later. That will involve some additional topics and some other things that we cover in typical pre-calculus courses that were not covered in this textbook, since this is just meant to be a brief overview of pre-calculus topics before jumping into calculus for those who need a refresher. So again, that was the purpose of these videos. I hope that they were helpful to you, either if you are a math tutor or a math student. Look forward to you in the next set of videos.